Hello, everybody. Today we'll be talking to you about our project, and that is snowfall patterns and the effects of snow cover in the Midwest. So the purpose of our paper is to investigate the key topics in each of our sections so we can compare our findings and speculate on the effects of changing snowfall patterns in the Midwestern United States. We broke our paper down into three different sections. A literature review was done to look at the effect of snow cover in the Midwest, such as the effect that it has on climate, hydrology, soil, and transportation-related issues such as car accidents and the cost of snow removal and salting of roads. Our next section focuses on the snowfall patterns in the Midwest as a whole. This was also done through a literature review. We looked at from the past up until present. This was pretty much from between the mid-20th century all the way up until now, and into the future, which is defined as the mid-21st century. Our third section took data from NOAA and ran statistical analysis on it to see what the trends in snowfall are locally in our area from 1950 all the way to 2019. The data that we used was collected at nearby Peoria International Airport.
This section examines the effect of snow cover on the environment and society, focusing on the Midwestern United States. Here we examine the effects of snow cover on climate, hydrology, soils, transportation, and we examine the effect of snow removal and the use of road salt. Snow cover's effect on climate is dependent on snow's albedo. Albedo is defined as the percentage of solar radiation that is reflected by a surface. Snow cover can have an albedo value as high as 90 to 95%, which is much higher than the albedo of a bare soil or vegetation. In the absence of snow cover, the radiation that would have been reflected by the surface is now absorbed by the surface. Therefore, a decrease in the amount of snow cover will cause a net increase in the amount of solar radiation that is absorbed by the surface, introducing more energy into the Earth's atmosphere system. Snow also has a large effect on air temperature. During the winter months, snow cover is responsible for 40 to 60% of air temperature variability in the continental United States. In the spring, this number rises to greater than 70%. Snowfall and snowmelt can also act as a fast climate switch by causing a shift in air temperature, either 10 degrees cooler or 10 degrees warmer, respectively. This concept is illustrated in Figure 3 from Betts et al. Pay attention to the first two graphs. The first graph demonstrates the change in temperature in response to snowfall. From the first snowfall, the graph shows a drop in air temperature which negatively correlates with snow depth. The second graph shows the same correlation, but in relation to snow melt and rising air temperatures. Snow cover impacts the hydrology of the Midwest through its role in peak streamflow, large runoff events, and groundwater recharge. An important concept to understand when discussing snow's hydrology is snow water equivalent. This is the amount of liquid water that is present within a snowpack. When a snowpack melts, the snow water equivalent of the snowpack is released as liquid water, which can either form surface runoff or infiltrate in a groundwater system. This depends on the timing of the snowmelt. If the snowmelt occurs when the ground is still frozen, meltwater will form surface runoff. If the ground is thawed during a melt event, some of the water will infiltrate the soil and enter the groundwater system. Sometimes, rain can fall on existing snowpack. This occurrence is called a rain-on-snow event and frequently contributes to flooding. Snow cover's effect on soils is largely due to the insulative effect snow has on underlying soils. Snow cover prevents the loss of heat from the ground by reflecting the ground heat flux back onto the soil. Additionally, snow cover's albedo dramatically reduces the solar radiation absorbed by the surface. These two properties effectively decouple soil under snow cover from the atmosphere. This insulative effect moderates soil temperatures, preventing freeze-thaw cycles and deep freezing events. Both freeze-thaw cycles and deep freeze events had negative consequences for the soil. The former breaks up soil structure, increasing the soil's vulnerability to erosion, reduces soil nutrient pools, increases greenhouse gas emissions from the soil, and reduces microbial activity in the soil. The latter also increases the magnitude of greenhouse gases released from the soil and can also kill biomatter within the soil from microbes to small roots. In addition to these environmental effects, deep freezing events can also cause damage to underground human infrastructure, such as water pipes. Snowfall has a dramatic effect on human transportation systems in cold climates. It can reduce commerce and the movement of goods and people due to the hazardous road conditions it creates. In response to this threat, our society has implemented snow removal methods and infrastructure such as snowplows and the use of road salt. Road salt is a very effective snow removal method that is relatively inexpensive and can reduce accidents by 87% on two-lane roads. Though road salt is effective, there are some serious drawbacks. Road salt is very corrosive to automobiles and transportation infrastructure such as roads and bridges. In the United States, road salt costs Americans approximately $11.8 billion annually due to vehicular corrosion alone. Road salt also has a negative effect on the environment. This chart shows as road salt enters the environment off roadways, it can affect water quality, plant and animal communities, and soil structure. This flow chart from Heinz and Relia demonstrates the movement of salt through the environment nicely.
Hi, in this section we'll be talking to you about past snowfall studies of the Midwestern United States. So the results from our literature review was that they all looked at snowfall totals and frequency from about the mid-20th century all the way up until present. Among all the studies, there was a clear consensus that there was an overall increase in snowfall frequencies and totals. Snowfall totals also varied based on latitude. So the southernmost extent of the Midwest received the less amount of snowfall, and the northernmost extent received the most. As I said, the northern extent of the Midwest experienced an increase in snowfall totals throughout this time period, and the far southern extent experienced a decrease in snowfall totals. The highest overall totals were recorded on the eastern side of Lake Michigan. This figure shows a map of the Midwestern United States and the study area that researchers looked at. It shows that in a local area of central Illinois, there was a positive % of snowfall per year, and this is the same throughout Iowa, both of the Dakotas, Minnesota, Wisconsin, Indiana, and Michigan, basically the majority of the Midwest. However, in Kansas and Missouri, it showed that there was an overall decrease in snowfall totals. So the causes of why there was an increase in snowfall totals during this time period was because of two reasons. The first is the lake effect snow. This is something that is very common in the Midwest and many people know about. It occurs when a cold, dry air mass passes over warmer water and moisture is then transferred to the clouds and in turn causes an increase in snowfall frequencies and totals on the easternmost edge of the lake that it's going over. This occurs mostly in Lake Michigan, where the eastern side of it, Michigan, receives a high amount of snowfall total and frequency per year. The next cause is an Alberta clipper. This is a very fast-moving low-pressure system that originates in the Canadian Rocky Mountains. This system brings gusty winds and colder temperatures to the areas and that it passes over, and it carries with a wide range of snowfall amounts. Usually it's between 1 and 3 inches per event, but at times it could bring a lot more.
In this local weather data analysis section, we will examine how snowfall trends have progressed locally in Peoria. For my local weather data analysis, I gathered the total amount of snowfall in inches for the winter months from the year 1950 to 2019. For the purpose of my analysis, the winter months is defined as October through April of the following year. I pulled all of my data from NOAA's online database using the weather station located at Peoria International Airport. Originally, my data was not normally distributed, meaning it followed a bell-shaped curve. Since we cannot perform statistical tests on data that isn't normal, I took the log of the total snow values, which made the data more normal. Now I can proceed with my statistical tests. I performed the Bruce-Pagan test to see if the data was homoscedastic, which means I was checking if snowfall was stable or becoming more and more erratic. Since I received a large p-value for this test, snowfall is not becoming more and more erratic over time. The figure you see on the right is a scatter plot of the normally distributed snowfall data. I also fitted a trend line in there to show a positive trend in total snowfall over time. Here we have a figure showing you the total snowfall values for each year's winter season. The blue line represents the total values in inches. As you can see, there does tend to be a variance in total snowfall from one year to the next, making many peaks and valleys in the figure. The red line is a trend line fitted to show the general pattern of snowfall from 1950 to 2019, and if you pay close attention, you can see a positive trend here as well. To make sure I wasn't including any extremes that would skew my results, I produced this graph here. Here we have the average snowfall for each year rather than the sheer totals. We also see a general ebb and flow in the blue line here as we did in the totals graph. The red trend line here also supports a positive trend overall. The conclusion from this figure is that over these 70-ish years, there is an overall increase in the average snowfall amounts. Finally, here we have a different type of graph. What is represented here is the deviation from the mean in total snowfall amounts for each year. The mean is 26.11 inches, so bars above the black line represent more snow than the mean, and below represents below the mean. As shown, the number of years below the average snowfall is about equal to the years of above average snowfall. Although, within the last 20 years, when the total snowfall is above average, the amount of which it is in surplus is becoming greater and greater. This may be an indication of climate disruption enhancing the extreme weather precipitation.
In this section, we'll be talking about the future of snowfall in the Midwest. So the predictions that the study made was that snowfall is projected to decrease in the majority of the Midwest through the 21st century. The main cause is that there is an increase in temperature due to climate change. Snowfall totals, like before, will vary by latitude. However, one study cited that snowfall totals have a chance to increase in portions of the Midwest. This is mainly in very, very high latitudes, such as northern North Dakota, northern Minnesota, and northern Wisconsin. Snowfall totals are expected to decrease by an average of 17.9 centimeters throughout the entirety of the Midwest. This figure shows 5 different inset maps that were included in the study. The first map shows the extent of the study area. The second map shows the elevation of the study area. The third map shows the observed snow depth in centimeters of the study area. The fourth map shows the simulated snow depth into the future in centimeters of the study area. And the fifth map shows the correlation coefficients between the two maps. As you can see in the observed snow depth in centimeters, northernmost extent of the region, so northern Minnesota, Wisconsin, and Michigan, all show around between 30 and 40 centimeters of snowfall. In the simulated snow depth into the future, This area, however, drops down to 10 to 5 centimeters of snowfall. As you can also see locally, Illinois is expected to decrease in overall snowfall totals as well.
Here is our conclusion. To conclude, here are some of our main points from our presentation as a whole. As Zach stated, the Midwest as a whole is expecting to see a decrease in snowfall overall. However, in the northernmost areas of the Midwest, we might see some increase in snowfall. In the case of Midwestern warming, there would be less snow on the ground, resulting in a decrease in the Midwestern albedo values. This would then propel the area into a positive warming feedback, resulting in more frequent freeze-thaw cycles. As Drew examined, frequent freeze-thaw cycles would have many negative impacts on human activity, including more prominent erosion and the releasing of more greenhouse gases. In the event of a snowfall decrease, the lack of rock salt would also decline, which possesses its own positives: less vehicle corrosion, less water pollution, and of course saving money. Through our local weather data analysis, the statistical tests and data patterns lead us to believe there is a positive trend that could progress into the future. However, since the data analysis was of Peoria snowfall only, these results cannot be applied elsewhere.